The prevailing consensus among scientists is that the Big Bang theory remains the primary explanation for the origins of the universe. This theory accounts for the creation of stars, planets, and all forms of life, including ourselves. Despite its somewhat misleading name, the Big Bang offers an intriguing glimpse into what might have occurred at the universe's inception. Initially, the universe was densely packed into a space smaller than a pinhead, with particles tightly compressed. From this tiny point, a monumental explosion of matter and energy occurred, known as the Big Bang. This event, occurring billions of years ago, paved the way for the vast cosmic history that we observe today. However, advancements in scientific understanding have led to growing inconsistencies with the predictions of the Big Bang theory. When NASA launched the James Webb Space Telescope, JWST, the most advanced space observatory ever built, scientists hoped its observations would confirm the theory. Surprisingly, after just 1 year in space, the JWST astounded researchers with its remarkable ability to peer deeply into the universe's past. Its groundbreaking capabilities revealed galaxies dating back to a time so ancient that it challenges our current understanding of the universe's beginnings. This discovery has sparked intense debates about what existed before the Big Bang. A significant moment in this research came when astronomer Rohan Natu, using data from the JWST, accidentally discovered a galaxy formed just a few 100 million years after the Big Bang, making it the oldest galaxy ever observed. This finding sent shockwaves through the scientific community, highlighting the telescope's extraordinary potential. Its mission to revolutionize our understanding of the universe is just beginning, promising to unlock unprecedented insights into the earliest chapters of cosmic history. The JWST's revelations challenge earlier assumptions, revealing galaxies that defy previous predictions. The unexpected abundance of early galaxies has prompted a rush of scientific inquiry, with experts working to reconcile these findings with existing theories. These discoveries raise fundamental questions about the nature of the universe and the forces that shaped its evolution. Moreover, the JWST's technology is revolutionary. Positioned 1.5 million kilometers from Earth, it is shielded from earthly interference and kept cool near absolute zero by its tennis court-sized sunshield. The telescope features a massive segmented mirror and highly sensitive instruments designed to capture details of the universe's earliest moments, what is known as the cosmic dawn. This epoch, which occurred a few 100 million years after the Big Bang, marks the formation of the first stars and galaxies. Researchers are still debating the factors behind this process, including the influence of dark matter, dark energy, and the interactions between starlight, gas, and dust. The telescope's observations of galaxies from the cosmic dawn offer an extraordinary opportunity for cosmologists to test their models. By examining these ancient galaxies, scientists can either confirm the accuracy of their current understanding or identify gaps that could lead to groundbreaking discoveries. Initially, it was expected that the JWST would only uncover a few faint, small galaxies during its early studies. However, the reality far exceeded these expectations. Its first images of the distant universe revealed a variety of galaxies with ages, sizes, and brightness levels that surpassed all predictions. This abundance of early galaxies has sparked a race among astronomers to claim new records for the oldest known galaxies, with new discoveries being announced regularly, leaving the scientific community in awe. These surprising discoveries have prompted speculation about whether there were flaws in the analysis of the JWST's initial data. However, most researchers agree that these findings signal a paradigm shift in our understanding of the early universe and provide tantalizing clues about the nature of cosmic evolution. Some scientists believe that these revelations could indicate that the universe is more complex and unconventional than previously imagined. This uncertainty raises fundamental questions about how the orderly universe we know emerged from the primordial chaos. The early discoveries from the JWST have the potential to reshape our understanding of cosmic history, offering insights not only into distant galaxies but also into the formation of our own Milky Way galaxy. As Mark McCarran, Senior Advisor for Science and Exploration at the European Space Agency, puts it, "You build these machines not to confirm the worldview but to break it. You just don't know how it will break." The origins of the JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At that time, G. Winger, then deputy director of STSCI, was tasked with imagining what would follow after Hubble. Despite initial reservations, Winger and a small team began laying the groundwork for what would eventually become the Advanced Space Telescope, now known as JWST. Unlike Hubble, which primarily observes visible light, JWST was designed to detect infrared radiation, allowing it to look much further back into the universe. This capability is essential for studying early galaxies whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its enormous cold, star-like mirror, JWST became the ideal tool for probing the mysteries of the cosmic dawn. The need for such a telescope was underscored in 1995, when the Hubble Deep Field observation revealed a multitude of galaxies in what was thought to be an empty patch of sky. This discovery highlighted the richness of the early universe and demonstrated the need for a telescope capable of delving even deeper into cosmic history. After more than 20 years of development and a cost of approximately $10 billion, JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of scientific observations, marking the start of a new era in space exploration. The early discoveries made by the James Webb Space Telescope, JWST, have greatly surpassed expectations, revealing galaxies that challenge existing models of the early universe. These surprising findings highlight the power of cutting-edge technology in scientific research, pushing the boundaries of our understanding. The initial goal of JWST was to explore the formation of early galaxies, and while the assumptions were modest, the results were groundbreaking. The JWST has already provided insights that have stunned astronomers, uncovering distant galaxies from nearly the dawn of time. Before JWST, the most distant known galaxy was GNZ11, discovered in 2015, with a redshift of 11, dating back to around 400 million years after the Big Bang. However, JWST's observations, led by Rohan Natu and his team, identified a galaxy named GLASS Z13 with a redshift of 13, placing it around 70 million years earlier in cosmic history than GNZ11. This discovery was made possible through improved techniques for assessing redshift, which, while less precise than direct measurements, allow for a quick estimation of a galaxy's distance. GLASS Z13 was found to be surprisingly bright and massive, already containing a stellar mass comparable to billions of suns, despite being significantly younger than the Milky Way. Subsequent observations revealed even more shocking findings. Galaxies with redshifts as high as 20 were detected, appearing just 180 million years after the Big Bang. Some of these galaxies displayed complex structures, a characteristic not expected to appear so early in cosmic history. Furthermore, evidence emerged for galaxies as large as the Milky Way at a redshift of 10, only 500 million years after the Big Bang. These rapid developments challenge the expectations of the standard cosmological model, known as lambda cold dark matter, lambda CDM, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, galaxies of such size and luminosity should not have formed so early in cosmic history. The formation of these massive galaxies in the early universe presents a significant puzzle for cosmologists. Understanding the early stages of the universe's development, particularly the first few moments after the Big Bang, is crucial to solving this mystery. Initially, the universe was a hot, dense soup of particles, and after millions of years, the first stars began to form, eventually leading to the creation of galaxies. This process is believed to have taken around 1 billion years. However, JWST's observations challenge this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of seeing smaller protogalactic fragments merging to form larger galaxies, as current models predict, JWST has identified galaxies that are already large and luminous. These findings are supported by other observations, such as those from the Atacama Large Millimeter Array, ALMA, in Chile, which provides further evidence for the existence of these distant galaxies and rules out the possibility of low redshift intruders. These groundbreaking discoveries open new avenues for understanding the early universe and may require revisions to our current cosmological models. JWST continues to challenge our understanding of cosmic history, testing assumptions and pushing the limits of galactic exploration. The absence of visible dust in the galaxies observed by ALMA highlights the difficulties faced by telescopes in confirming JWST's findings. While JWST can cross-check its own observations, confirming these discoveries with other telescopes is a challenge. The implications of JWST's observations are profound, potentially challenging the lambda-CDM cosmological model and prompting updates to our understanding of the universe. Some scientists, like Michael B. and Cullen, have expressed amazement at the findings, suggesting a significant departure from our current cosmological knowledge. One possible explanation for these discoveries is the modified Newtonian dynamics (MOND) theory, which questions the existence of dark matter and offers alternative explanations for the gravitational effects observed in these galaxies. JWST's findings align with the expectations of MOND advocates, such as Mark McClock, who view this as further evidence supporting the hypothesis. However, some researchers like JACYP remain skeptical and point out the challenges of reconciling MOND with existing data. Another possible explanation for the brightness of these galaxies could be the lack of dust in the early universe, which would make them easier to detect, potentially complicating efforts to measure their masses accurately. Andrea Ferrara suggests that dust might not have had enough time to form in the early universe or could have been expelled during galaxy formation. Charlotte Artisan and her colleagues propose that JWST may simply be detecting the brightest young galaxies, which are easier to spot. David Spergel hypothesizes that efficient star formation in the early universe could explain the observed brightness of these galaxies. He suggests that early magnetic fields might have played a role in triggering star formation, providing a possible explanation for the rapid growth of galaxies in the early universe. The rapid flow of scientific papers stemming from JWST's initial observations underscores the importance of these discoveries and the profound implications they have for our understanding of cosmology. As researchers continue to explore JWST data, they may uncover even more insights that challenge and expand our current models of the universe. When the first data began to be released from JWST, astronomers were eagerly awaiting the results. Many had spent years preparing their data analysis pipelines in anticipation. Instead of following the traditional peer review process, which can take months, scientists opted to publish their findings on AR14, a platform where scientific papers can be uploaded for quick review and discussion. This approach allowed for a faster dissemination of discoveries, with public discussions taking place in real time on social media platforms like Twitter. Rohan Nata referred to this as science by spectacle, and the subsequent wave of conversation was intense and surprising. However, there are concerns about the potential drawbacks of this rapid dissemination of findings. Some scientists like Klaus Pontypool, a JWST project researcher, acknowledge that while the quick sharing of results allows for prompt public discussion, it also carries the risk of rushing the scientific process.